Alright, so we're now going to start our second video on rational functions. And as was mentioned in the previous video, what we're going to primarily focus on in this one is vertical and horizontal asymptotes. Now we're going to focus on the definition of these vertical and horizontal asymptotes and how to find out if something is a vertical or a horizontal asymptote. Alright, so let's talk about the definitions here first. So the line x equals a is a vertical asymptote of the graph of f when f at x approaches infinity or f at x approaches negative infinity as x approaches a either from the left or right side. And just to kind of give you this here, this is basically thinking that it's not necessarily defined at a, but basically as you get close to this x value a, this vertical line here, either on the left or right hand side, or maybe on both sides, it approaches either infinity or negative infinity. And that's what gets you a vertical asymptote. Now there will be an easy way to determine what vertical asymptotes we have when looking at rational functions. But vertical asymptotes aren't just reserved for rational functions. There will be some other functions we look at in this course that will also have vertical asymptotes that are not rational functions. Alright, so let's do the horizontal asymptotes. So the line y equals b is a horizontal asymptote of the graph of f when, well, in this case, f of x isn't approaching positive or negative infinity. It's actually approaching this, not equals, it's approaching this value b, this line y equals b, when or it technically shouldn't be the word when, it should be as. Come on. As x approaches infinity or x approaches negative infinity. Now before we talk about this or even look at some graphs, there's some key things. Well, maybe let's look at some graphs first and then we'll talk about some key things about what you can have as far as horizontal and vertical asymptotes. So let's see here. It looks like my graph here isn't pasting anymore, so I'm going to have to redraw it. I'm going to just pause the video recording here so I can redraw it. Okay, so two graphs magically appear now because I paused the recording here. So I want to just draw a couple sketches here to kind of illustrate both horizontal and vertical asymptotes. So typically when we're sketching some of these, we'll often have a dotted line drawn in here. And when you see a dotted line, that's not part of the graph. And in this case, with the graphs that I'm drawing, these are going to be vertical asymptotes. And then I'll go ahead and draw a horizontal line as well. Okay, so if we draw an example of a function here, maybe it looks something like this, and then something like this, and something like this. So in this graph right here, what we have is that x equals -2 and x equals 3 are vertical asymptotes. And I'll often abbreviate that as just VA for vertical asymptote. And you're welcome to do that abbreviation as well. Now, I just want to kind of emphasize why that's the case. If we go back to the definition here, clearly this is the x equals -2 right here, and it says from the left or right hand side. So from the left hand side, I'm going up, this is going to keep going up to positive infinity. So I want to emphasize right now that there alone makes that a vertical asymptote. So it's not saying that both sides have to go to infinity. As long as one side goes to infinity, that makes it a vertical asymptote right there. But then if we look at the other side, it also fits the definition here. So it goes all the way down to -infinity. So that's also giving us that this is a vertical asymptote, but just once again emphasizing one of these yellow highlights only has to be present in order for it to be a vertical asymptote. And then going to x equals 3, we can clearly see I've got the same idea here. They're going both down to -infinity. So one side is going to infinity, which is all that matters. And then if we think about, well, as you're going to positive infinity, x is going to be going up here, and it keeps getting closer to this line y equals 2. And if I go to the -infinity, I have the same thing. It's going closer and closer to y equals 2. So we have a horizontal asymptote of y equals 2 is a horizontal asymptote, which again I will abbreviate as HA, and you're welcome to as well. So let's look at another one here. I'll draw some dotted lines in, then make a sketch. Alright, so I'm going to now sketch a function in here. So let's sketch, I'm just making this function up, not necessarily thinking too much about it. And so this is the function I've sketched. And what we can clearly see here is that if we talk about vertical asymptotes, we have x equals -1 and x equals 4. And then if we're talking about horizontal asymptotes, we have 2, and this would be y equals 1 and y equals -2. Now I want to just emphasize the horizontal asymptotes here, because we have 2 because, well, here, my highlighter would select here, when I'm going to negative infinity, I keep getting closer and closer to y equals 1. So that makes that a horizontal asymptote. But then as I go to positive infinity, I can keep going to y equals negative 2. And so that makes it a horizontal asymptote as well. Now, one thing here that I'm going to highlight, or at least make a note of, is you can have at most two horizontal asymptotes. Now, typically with rational functions, you're only going to have one horizontal asymptote, but you can have at most two horizontal asymptotes, and I should maybe put in a little bit of this for functions. And the reason you can't have more than two for functions is that if you think, well, the definition said it was as you're going to positive or negative infinity, and so, well, that only gives you two possibilities. Otherwise, you wouldn't pass your vertical line test. But then you can have any positive integer number of vertical asymptotes. Now, it also turns out you can also have an infinite number okay, let me pause it again. Oh, there it goes. Infinite number of vertical asymptotes. Now, we won't see any functions where in this course where we have an infinite number, but if you take a trig course at some point, really early on in the semester, when you start looking at graphs of some of the trig functions, you'll wind up with several of them. In fact, 4 of the trig functions that you will look at, 4 of the 6, have an infinite number of vertical asymptotes when you look at their graphs. All right, so let's talk about how to find these here. So, vertical asymptotes. Let's talk about how to find vertical asymptotes. Well, I'm going to emphasize possible vertical asymptotes are, it's doing its weird thing again here, are x values that make your denominator, remember the denominator we've been representing as d at x, equal to 0. Now, I want to emphasize that I said possible vertical asymptotes are x values that make d at x equal to 0. So how do we know which ones are the actual ones? Well, the way I like to think of it is that if you simplify / reduce I'll just leave that there. F at x as much as possible, the vertical asymptotes are the x values that make the reduced version denominator 0. So let's look at a couple examples here illustrating this. First one, let's just start with an easy example here. So these are all going to be find the vertical asymptotes. So let's start with, as I said, a fairly straightforward function, and this is x over 3x plus 1. Now, it says that if you want to find the vertical asymptotes, you should simplify or reduce this as much as possible, but there is nothing we can do here. There's no common factors in the numerator or denominator. Don't get tempted to cross these x's out. You can't do that because, of course, there is a plus here. So it's got to be a factor of your numerator and denominator in order to reduce it or simplify it out. So there's no simplifying or reducing out that you have to do, and so then my vertical asymptotes are going to be when 3x plus 1 equals 0, and so then we just solve this for 3x equals negative 1, x is equal to negative 1/3, so my vertical asymptotes are x equals negative 1/3. Notice also that the vertical asymptote is occurring at x values that aren't in the domain of f of x. And that's going to be true for all rational functions, that any vertical asymptotes are going to be at spots where the function is not defined, or at x values that aren't in the domain. Now, you might be saying, well, can't I just plug in and see whatever makes the denominator 0, and those are my vertical asymptotes? And the answer to that is no. You can't do that because, as I said, you have to have it simplified down as much as possible. And an example to illustrate this, let's look at g at x is equal to x squared minus 4 over x squared plus 3x plus 2. Now, if we just looked at the domain here, so let's look at the domain first. So my domain, of course, is all real except what makes the denominator 0. So let's look at what makes the denominator 0. So we have x squared plus 3x plus 2. And what this actually factors to would be x plus 2, x plus 1. And so we set that equal to 0. And we get that x is equal to, of course, negative 2 and negative 1, which means the domain is all real numbers except x equals negative 2 and negative 1. So that is absolutely correct with what our domain is. Now, we will finish this problem out here, but it turns out, I'll give you the answer here, this is x equals negative 1 is the only vertical asymptote. X equals negative 2 is not a vertical asymptote. And if you were to look at the graph of this, which we'll be looking at these in the next section, this actually corresponds to what we call a hole in the graph. So it's not a vertical asymptote, but actually corresponds to a hole. And to see what's going on here, as I said, what do we need to do to find vertical asymptotes? We look at g at x, but we simplify or reduce it. So the numerator factors to x minus 2, x plus 2, and then of course we already know what the denominator factors to. It was x plus 2, x plus 1. And so if I reduce this down, now I'm not going to write g at x is equal to this because it's not, because g at x is this original function. You can't cross out the x plus 2's. That's part of the original function. But we can say here that it reduces to x minus 2 over x plus 1. So then the vertical asymptotes are x equals negative 1, because that's now the only thing that makes the denominator 0. So it's not the same as the domain. Your vertical asymptotes aren't necessarily the same as your domain. Now, in a lot of cases, it will be the same as your domain, but it's not guaranteed. So that's why you should always, when you're looking for vertical asymptotes, first ask yourself, can you factor and reduce the rational function? And if you can, you want to do that first, then find what makes your denominator 0 in those reduced forms. All right, so let's talk about how we can find the horizontal asymptotes. So horizontal asymptotes, well, some texts like to come up with this elaborate kind of way of finding it. I just like to think of it as this way, is that the horizontal asymptotes, rational functions end behavior follows the lead terms of numerator and denominator. So let's look at a couple examples and see how this can kind of quickly tell us what the horizontal asymptotes are. So find the horizontal asymptotes. All right, I suppose that should give us a function here. So let's look at f of x is equal to 3x squared minus 2x plus 1 over x squared plus 5x minus 10. And so if we're trying to find the horizontal asymptotes, I look at the two lead terms. Well, the lead term in the numerator is 3x squared, and the lead term in the denominator is just x squared. Now, so the end behavior of f of x follows 3x squared over x squared. But then just simplify this down. 3x squared over x squared is just what? Simplified down is just 3. So the end behavior follows 3x squared over x squared, which is equal to 3, which this tells me then my horizontal asymptote is y equals 3. Now, some texts like to say, well, if the degree of the numerator is the same as the degree of the denominator, it's the ratio of the lead terms and everything else like that. And while that's technically correct, there's so many cases you have to remember. To me, I just say, well, let's look at the lead terms and then just think about what that means. So the lead terms here reduced down to 3, so that would just mean I have a horizontal asymptote of y equals 3. Now, before we do another example here, the reason we can ignore all the other terms when we're looking at end behavior is we're talking about when x is really big. And you think about this in terms of money, for instance. You know, if you had, like, for instance, x squared being, now let me just do a couple quick computations on my calculator here because my arithmetic isn't going very well here. So let's say x represented money, for instance, and let's say x was 1,000. If x was 1,000, we'd have x squared is 1 million, so 3 million. So imagine, okay, you have $3 million, and then you have to spend 2 times x, so 2 times 1,000. You have $3 million, and you have to spend $2,000. Are you really going to notice $2,000 if you had 3 million? You know, I mean, technically, yeah, you've lost some money, but you really don't notice that. And it just gets more to the point here, well, I get larger values and now take a million squared. Well, a million squared versus, you know, just a million, well, a million squared is actually going to be 1 times 10 to the 12th power versus 1 times 10 to the 6th. So, you know, you're just, as you get higher and higher, these x squared terms are going to dominate. And that's going to be true no matter what the rational function is. Whatever the highest degree term is in your numerator, that's going to be what's going to be the dominant term in the numerator. So let's look at another example here. So let's look at g at x is equal to x squared minus 3x plus 1 over 3x cubed plus 5x minus 2. So the end behavior follows, well, you need the lead term in the numerator, lead term in the denominator. Lead term in my numerator is x squared. Lead term in the denominator is 3x cubed. Now, lead term doesn't necessarily mean first. It's highest degree term. Now, of course, we typically always write these in descending order, but maybe a homework problem, they're purposely trying to trick you, and they might write, for instance, negative 3x plus x squared plus 1. X squared is still the lead term, even though it wasn't written first, because the lead term is always referring to highest degree. So the end behavior follows x squared over 3x cubed, which this reduces to, well, I could cancel an x squared out of both, and so I'd have 1 over 3x. Now, that's not a horizontal asymptote, 1 over 3x. Horizontal asymptotes are numbers, y equals some number. Well, what we have to ask ourselves is, what happens as x goes to infinity or x goes to negative infinity? And one way to kind of see this, anytime you have x in a denominator with a positive exponent there, it's actually always going to go to the same thing. It's going to go to 0. Because, for instance, if you were to just do some simple computations with the positive one, if you did x equals 10, you'd have 1 over 30. X equals 100, 1 over 300. X equals 1,000, 1 over 3,000. And 1 over 30,000. So on and so on, if I keep putting bigger numbers. But then if I were to do these decimal numbers here, this is 0.03 repeating, this is 0.003 repeating, this is 0.0003 repeating, so on and so on. So these numbers keep getting smaller, and they keep getting closer to 0. So we have a y equals 0 as a horizontal asymptote. Now there's one more I'd like to look at here. And this is a little bit longer video, but that's okay. Let's look at h at x equals x cubed plus x squared over 3x squared plus 1. So again, looking at my lead terms here, I have x cubed and then 3x squared. And so the end behavior is going to follow x cubed over 3x squared, which reduces to x over 3. Now again, I can't just say y equals x over 3 is my horizontal asymptote. Horizontal asymptotes are numbers. Well, so we need to say, well, what happens as x goes to infinity or x goes to negative infinity? Well, as x goes to infinity, x over 3, well, this is actually going to go to infinity as well. I mean, x over 3 is just a straight line with a slope of 1/3. And so then if x goes to negative infinity, x over 3 goes to negative infinity. So what does that mean as far as my horizontal asymptote? Well, what this means is that h at x has no horizontal asymptote. You don't have to have a horizontal asymptote, and in this case we don't. Okay? So that's going to wrap up this video here. I'm going to do one more video just introducing rational functions before we get to the graphs. But this next video that you'll see is actually, it's going to be very short. It's going to be like 1, maybe 2 example problems of some story problems.